Hi students. So now we are going to see the topic invertible and non-invertible systems. Non-invertible systems. Okay. So what is an invertible system? So what is an invertible system? Which one is called as an invertible system and which one is called as a non-invertible system? Okay. So invertible system. A system is said to be invertible. A system is said to be invertible if the input of the system appears at the output. If the input of the system appears at the output. That means if we are given an input as x of t and if the output of the system also at the end will get same x of t, then I can say that system as an invertible system. For your better understanding, I will explain invertible system like this. If there is a ineq relationship between input and output, then the system is invertible. If there is only ineq relationship between input and output, that is for input and output there will be ineq. There is one-to-one relation. Hence it is nothing but one-to-one mapping. If there is a one-to-one mapping between input and output, then we can say that system as an invertible system. So I had given two definitions for invertible system. You can write any one of your choice. Which one you are easy, you can go that one. First one, invertible system. A system is said to be invertible if the input of the system appears at the output. If the input of the system appears at the output, then we can say that system as an invertible system. That is, the output of the complete system must be an input. So if you give the input as x of t, you are given the input as x of t to something. There is a composite system which consists of two small systems inside this, and finally at the output also, if you get x of t, then we can call that system as an invertible system. That is, a system is said to be the invertible system if it has ineq relationship between input and output. Let us take this is x of t and here y of t. If between x of t and y of t, that is input and output, if there is only ineq relationship, that means there is only one-to-one relation. That is one-to-one mapping. A system is said to be the invertible system if there exists an ineq relationship between input and output. Okay, so whenever there is only one-to-one mapping between the input and output, then we can call that system as an invertible system. So see, for understanding one-to-one mapping, let us take two sets like this. Here I have 1, 2, 3. Here I have A, B, C. So this is our input x of t, and consider this is our output y of t. Now this one is mapped to B. Okay, 1 is mapped to B, and 2 is mapped to A, and 3 is mapped to C. Okay, see, here is only one-to-one mapping. 1 is mapped to B, 2 is mapped to A, and 3 is mapped to C. That is only one-to-one mapping. That is the ineq relationship between input and output. So for one input there is only one output. So we have the separate inputs, we have the separate outputs. That is ineq relationship between input and output. That is one-to-one mapping. Those type of systems are called as invertible systems. Okay. Now coming to the non-invertible system. So complete opposite of the invertible is nothing but non-invertible. Opposite of invertible means a system is said to be non-invertible. A system is said to be non-invertible if the input of the system does not appear at the output. If the input of the system does not appear at the output, that is, output is not equal to the input. Okay, those systems are called as non-invertible systems. A system is said to be non-invertible system if the input of the system does not appear at the output, then we can say those type of systems as non-invertible systems. Or simply, if a system is said to be the non-invertible system where does not have a unique relationship between input and output. It does not have a unique relationship between input and output. Does not have a unique relationship between input and output. So for a system, if there is no unique relation between input and output, then we can say that system as a non-invertible system. Does not have unique means, so you can explain with the example as many to one mapping. That is many to one mapping. That is, for 2 or 3 inputs, if you have only one output, for 2 or 3 different inputs, we have only one same output, then those type of systems are called as non-invertible. That is, here let us take for input x1 of t, x2 of t, etc. There are 3 different inputs. I have only one output for x1 of t, for x2 of t, for x3 of t. There are 3 different inputs. The system is producing the same output y of t. It is producing only one output y of t. For x1 of t, it is producing y of t. For x2 of t, it is producing y of t. For x3 of t is also it is producing y of t. Then those systems are nothing but non-invertible systems, because here at the output we are not getting the input. That means the input of the system does not appear at the output, first point, and there is no unique relationship between input and output. There is no unique relationship between input and output. That is, there is many to one mapping. That means for different inputs, the system is producing the same output. So those systems are called as non-invertible systems. For this also you can go for the mapping. So I will explain that with the help of a mapping. Non-invertible. Consider set 5, 10, 15. So this is x of t and y of t equal to x, y. For 5 we are getting y, and for 15 also I am getting y. Only for 10 I am getting x. See, for 5 and 15 I am getting as y. For 10 only I am getting as x. That is, here many to 1. So 5 and 15 is mapped to y only. Okay, y only. So you can take only y is here, and if 5, 10, 15 all are mapped to only one thing also. Okay, so another example also you can go for this one. 2, 4, 6 and z. 2 is mapped to z, 4 is mapped to z, 6 is mapped to z. So this is nothing but many to one. So for these many to one systems, we can call that as an non-invertible systems. So if there does not have an unique relationship between input and output, then we can say that system is an non-invertible system. See, here we have a unique relationship. Here we doesn't have a unique relationship. That means here for input A we have output B. Input 1 we have output B. Input 2 we have output A. Input 3 we have output C. So for each and every different inputs we have different outputs. There is a unique relation between input and output. Coming to this one. Here if the input is 5, output is y. Input is 10, output is x. Again input is 15, output is y. That is, for 5 and 15 the output is y. That is, for different inputs we are getting a same output. That is, there is no unique relationship between input and output. Or this, take this one, 2, 4, 6 all are mapped to z. That is many to one mapping. That is, for 3 different inputs I am getting the same output. So we can say that whenever we doesn't have a unique relationship between input and output, we can say that systems as non-invertible systems. So with this, I hope you have a clear idea what is invertible and non-invertible. I can give some more examples also. Let us consider x of t like this. Let us consider x of t and y of t. Okay, and the given function is y of t equal to x square of t. Y of t equal to x square of t. Let us take my input x of t. So here the function is y of t equal to x square of t is the function. Y of t equal to x square of t is the function. For that, first I am considering the input as in place of x of t I am taking 2. So what is y of t? Taking x of t as 2. What is y of t? Y of t is 2 square. 2 square is 4. Okay, can write as 4. Now again I am taking another input. Here the another input x of t as minus 2. X of t as minus 2. Then what is the output? Minus 2 whole square. Minus 2 whole square is also 4. Again this is also 4. That is, for 2 we are having the output as 4. For minus 2 also we are having the output as 4. That is, for 2 different inputs I am having the same output as 4. I am having the same output as 4. So for 2 different inputs I have only one output. So that is, there is no unique relationship between input and output. There is many to one mapping. Hence we can say those type of systems are non-invertible. That is, here we can't get what is the exact input for the output. For they are given the output as 4. So we doesn't know what is the exact input. That is either plus 2 or minus 2. We doesn't know for this example what is the exact input. So for the output we have 2 inputs. So we doesn't know the exact input. That is, the input is not exactly occurs at the output. That is, the input of the system does not appear at the output exactly, because for different inputs we have the same output. So the exact input of the system does not appear at the output. So these are nothing but examples of non-invertible systems. So example for non-invertible is y of t equal to x square of t. So you can go for many examples like that. So I will explain the examples within a few minutes. Okay, I hope now you are all clear with invertible system and non-invertible system. I had given the definitions, 2 definitions, and explanation like 1-to-1 mapping and many-to-one mapping, and I have gone for that some diagrammatic explanation, tabular forms and equational, everything. Okay, now I will explain this with the form of a block diagram also. Okay, now I will explain invertible and non-invertible system with this simple block diagram. Okay, so before that I gone for the sets, a mapping, 1-to-1 mapping, many-to-one mapping, and some equations, some tabular columns. I explained everything about invertible and non-invertible. Okay, now I am again explaining invertible and non-invertible using simple. See, in the diagram we have an input x of t, and that input is given to a composite system. That means here this system consists of 2 small systems inside it. The composite system consists of 2 small systems. So first one, okay, system. Actually this is an invertible system. And the second one, it is inverse system. The second one is inverse system. Okay, so 2 things. The first one is invertible and next one is inverse system. Now if this composite system is completely as a single one, we have to treat this composite system completely as a single one. Okay, now we have to say this composite system as a invertible system or non-invertible system. First thing, I will give the input to a system. Okay, I pass this. Now the output of the system is some, let us consider as y of t. Y of t. So how can you write? How can you write y of t? In general, y of t I can write as transformed version of x of t. Y of t is nothing but the transformed form of x of t, transformed version of x of t. So here I am go for transform. I am transforming x of t to y of t. That the system is transforming x of t to y of t. Now coming to the inverse system. What the inverse system will do? It has to go for inverse transform. As x of t is converted to y of t, this inverse system has to convert that y of t into x of t. So this is an inverse system. So it has to go for inverse transformation, inverse transforming. So what I can write? Here I can write T inverse. T inverse. T inverse means it will go for the inverse transformation of the input that I have given to this one. So the input of this one is y of t. I have to go for inverse transformation. That is, y of t is to be transformed to x of t. Y of t has been transformed to x of t. So that is, here the output is again x of t. The output is again x of t, or simply we have to consider this output as z of t. You can consider it as z of t. Okay. Now this z of t will be equal to our x of t, because this z of t is inverse transformation of y of t. Inverse transformation of y of t is nothing but our x of t. So you can write this in the form of an equation. You can write this in the form of an equation. Okay. How will you write it? So here I am going for the inverse transformation. Okay. First, inverse transformation of y of t. Inverse transformation of y of t. Inverse transformation of y of t. What is actually y of t? Y of t is this one, transformation of x of t. So you can write, inverse transformation of y of t is nothing but transformation of x of t. So this is the one. What we get at the output. What we get at the output. Okay. So this is inverse transformation of x of t. This is what we get at the output. What we get at the output at this point. Okay. What we get at this point. So here, what we get? This one. That is inverse transformation of y of t. Y of t is transformation of x of t. Transformation of x of t. Clear? I hope you are clear with this one. Okay. Transformation of x of t. Now see, this inverse transformation of x of t is equal to x of t. Is equal to x of t. These both are equal. These two are equal. These two are equal. Okay. Then I can say the system is a invertible system, because on performing the operations I get the input of the system at the output. Input of the system at the output. So we can say this as invertible system. So we can say like this. If this one is equal to x of t, this one is equal to x of t, then I can say this as an invertible system. Okay. So by this small block diagram and small equation representation also, I can explain what a invertible system is. Okay. So see, once again, here I had given the input x of t to a system. That is, it is transforming this x of t into y of t. So the output of the first system in that composite system is y of t. Again, that y of t is given to another system, which is nothing but an inverse system. Inverse system. So there I go on for the inverse transformation. Now what it will do? Inverse transformation of the input of that system, that is y of t. Inverse transformation of y of t. Now inverse transformation of y of t is nothing but the transformation of x of t. So output of the second one, that is the output of the composite system, is inverse transformation of x of t. If that value is equal to the input x of t, then I can say that system as an invertible system. Then I can say the system as invertible system. First thing, if this inverse transformation of x of t, inverse transformation of x of t, x of t is not equal to the input x of t. Inverse transformation of x of t is not equal to the input x of t, then I can say this system as non-invertible. And if this will be equal to this one, then I can say this as invertible. Okay, invertible. So this is regarding invertible and non-invertible systems. Okay, so if you want to write the diagram for non-invertible, so I have to write the complete diagram again. So if you want to write x of t, it's a composite system, or simply inside there is a system transformation. Okay, transformation, and that is given to inverse transformation. Okay, and the output, so output, what it is? Inverse transformation of our x of t, if hold this value, okay, is not equal to x of t, then I can say this system as a non-invertible system. You can say this system as a non-invertible. If it is equal, then I can say it is an invertible system. So this is the block diagrammatic representations for invertible and non-invertible. So finally I can say the equation format. So in the equation format, finally I will give inverse transformation of x of t is equal to the input x of t, then I can say this system as invertible. This system as invertible system. Okay, if inverse transformation of x of t is not equal to the input x of t, then I can say the system as non-invertible. So this is regarding invertible and non-invertible systems. Okay, I explained you with the table column mappings, one-to-one, one-to-many, and small block diagrams and equation format. So I hope you are all clear with this invertible and non-invertible systems. Now I will see a few problems regarding this invertible and non-invertible system. We will give a few problems. That is, they will give some equations. So we have to find out whether those equations are those system equations represents either invertible or non-invertible. So we move on to the problems. With respect to invertible and non-invertible systems. Okay. Now we will see the problems regarding the invertible and non-invertible systems. So there is three system equations. We have to verify whether the system equation represents an invertible system or non-invertible system. So the system equation represents an invertible or non-invertible system. We have to find out. So we'll start with the first one. So what is the first one? The first one is y of t equal to 3 into x of t. See, on observing itself, I can say there is a one-to-one mapping. Why? Because so for each and every input, I will get different outputs. Okay. So for different inputs, I will get the different outputs. So directly I can say as this is an invertible system because there is a unique relationship between input and output. So for your understanding, I will take examples as x of t. equal to 1 and x of t equal to 2, x of t equal to 3, x of t equal to 0, x of t equal to -1. You can take any values, n number of values. So what is y of t for this one? It implies y of t equal to, what is y of t? 3 into 1, 3. What is y of t here? 3 into 2, 3 into 2, 6. Y of t, 3 into 3, 9. Y of t, 3 into 0, 0. Y of t, 3 into -1, -3. So see, there's an inequal relationship between input and output. If the input is 1, output is 3. Input is 2, output is 6. Input is 3, output is 9. Input is -1, output is -3. So that is 1-to-1 mapping. That is, you can get the input of the system at the output. Okay. So this system is an invertible system. So you can say this system as an invertible system. Simple logic. Okay. So we have an inequal relationship between input and output. For different inputs I am getting different outputs. That is 1-to-1 mapping, and by this we can get the input of the system at the output. So this system may be called as invertible system. So by using the equation, if I know the output, I can directly find out what exactly the input is. If I know the output as 6, okay, 6, then what is the exact input? Bring this side. 6 by 3 is 2. That is, input is 2. So if I know the output, I can get the exact input of the system. Hence, this system is an invertible system. Why? Because by knowing the output, I can get the exact input. That is, I can get the input of the system will appear at the output. So I can say this system as an invertible system. Okay, now move on to the second example. That is the second one, that given y of t equal to 2 into x square of t. 2 into x square of t. Clear? 2 into x square of t. Now see, here also we will take different examples. That is, different parameters. Say, let's consider x of t equal to 1, x of t equal to 2, x of t equal to -1, x of t equal to -2. So when x of t equal to 1, what is the y of t? It implies y of t equal to 1 square is 1, 2 into 1, 2. Next, 2 square is 4. 4 into 2, 8, -1 whole square is again 1. 1 into 2 is again 2. And the last one, -2 whole square. -2 whole square is nothing but +4. 4 into 2 is 8. So y of t equal to 8. See, for the inputs x of t equal to 1 and x of t equal to -1, I am getting the same outputs as +2. For the inputs x of t equal to 2 and x of t equal to -2, I am getting the same outputs as 8. Okay, that is, for different inputs I have only the one output. That is, for input 1 and -1 I have the output as 2. For input 2 and -2 I have the output as 8 according to the given system. That is, there is many-to-one mapping and there is no unique relationship between input and output. That is, we can't get the exact output at the exact input. We can't get the exact input at the output of the system. That is, if I know the output, I don't get the exact input. Here, let's say I know the output. Here, if I know the output, y of t equal to 8, then what? Y of t equal to 8. Then what is the exact input x of t? You can't say. It may be +2 or it may be -2. So you can't say the exact input. So there is no exact relationship between input and output. There is no unique relationship between input and output. That is, the input of the system does not appear at the output exactly. So you can say the system is a non-invertible. This is invertible. Okay, so the previous example is invertible, and what I explained now is an non-invertible, because see, for the first one there is a unique relationship. Okay, and for different inputs we are getting different outputs. There is a one-to-one mapping, and I can get input will appear at the output. That if an output is given, I can know the exact input. For that reasons, I can say this, the first one as invertible system. Coming to the second one. So what I will go for the second one. So the second one, y of t for different inputs. For different inputs, I have the same output. That is, if there is many to one mapping. That is, there is no unique relationship between input and output. That is, the input does not appear at the output. Or if you know the output, I can't get the exact input. Hence, the system is non-invertible system. Now coming to the third one. Yeah, here the important one. See, here the third one is y of n. See, third one is y of n equal to x of n plus 2. Now my question is, here this system equation with respect to continuous and discrete. So this system equation is with respect to discrete. Now up to now I explained everything in terms of continuous. Why? Because you are all familiar with the continuous time signals rather than the discrete signals. Hence I explained everything about continuous time. Now if I want to explain the concept with respect to discrete, the concept is same, only the change is the variable t will be replaced with the variable n. That is the only change, except that everything are same. So before solving this problem, I will ask you one thing. Okay, Now, what will be the input of for and discrete time system? The input will be represented with x of n. Input is represented with x of n. Now, this is given to a composite system. Inside this, we have system, transfers, and the output of this one is considered as y of n, and that is given to another system, that is inverse system. Now what will be the output of that one? We can say as z of n. If this z of n is equal to x of n, that is output input of the system appears at the output, then I can say this is an invertible system with respect to discrete. If z of n is not equal to x of n, the output of the system is not equal to x of n, that is, input does not appear at the output, then I can say that is an non-invertible system with respect to discrete. Now anyone write in terms of equations. Equation format. So how can you write this one? Inverse transformation of input x of n. Inverse transformation of x of n. If this value is equal to x of n, then I can say that system as an invertible system with respect to discrete. Say the output is inverse transformation of x of n. If this value is not equal to x of n, that value is not equal to x of n. Okay, if that value is not equal to x of n, then I can say that system as non-invertible system. So these two are the equational representations for invertible and non-invertible with respect to discrete. So what I did here, just I replaced the variable t with the variable n. T for continuous time, small t for continuous time, and small n for discrete time. So from now onwards, I will explain maximum part with respect to continuous time signals. So you can apply that to discrete also by replacing small t with small n. So whenever the concept is same, just replace small t with small n. So 2, based on the time constant, I will explain more concepts with respect to continuous time. Why? Because these continuous time are very familiar with you. Okay, understanding of the familiar topics is better when compared to the understanding of new topics. Discrete is a new topic, so I will explain with in terms of continuous. Hence, in the previous class also, first I will go with the continuous. At the end, I will go for discrete. So here also I explained. Right from next class onwards, if I gone with the continuous time signals, you can do for the discrete time signals just by replacing the small t with the small n. Okay, I hope. So now from now onwards, you don't get confused with the continuous time and discrete time. So continuous time is input is x of t and output is y of t, whereas discrete time input is x of n and y of n. The concept is same. See, now based on this, solve the equation. Solve this equation. Okay, for discrete time system. So how will you solve? Same, the concepts are same, one-to-one mappings, everything is same. So here also, if you go for one-to-one mapping or many-to-one mapping, so for different inputs, if you get the different outputs, that is, there is only one-to-one mapping and there is a unique relation between input and output, then I can say that system as an invertible system with respect to discrete. Let us take the equation. In this equation, let's, so they had given y of n equal to x of n plus 2. Let x of n equal to 1 and x of n equal to 2, x of n equal to minus 1, x of n equal to minus 2. I have taken 4 examples. So for x of n equal to 1, what is the output? What is the output? Y of n equal to 1 plus 2, 3. For x of n equal to 2, y of n equal to 2 plus 2, 2 plus 2, 4. For x of n equal to minus 1, what is the y of n? Minus 1 plus 2, minus 1 plus 2. So, what is the y of n? 1, that is 2 minus 1, that is 1. Next, for x of n equal to minus 2, x of n equal to minus 2, what is the y of n? Minus 2 plus 2, 0. Or you can take x of n equal to 0, x of n equal to 0. And what is y of n? 0 plus 2, 2. That is, for different inputs, I am getting the different outputs. That is, there is only one-to-one mapping. One-to-one mapping. That is, there is an unique relationship between input and output. That is, the input will appear at the output. The system input will appear at the output. That is, if I know the output, I can get the exact input. If the output is 9, what is the exact input? So bring this side, 9 minus 2, 7. So x of n is 7. So if I know the output, I can get the exact input. There is a one-to-one mapping and there is a unique relation between input and output. Hence, this system is nothing but invertible system. This system is invertible system. So for your practice, I can give one more example. Okay, simply y of t or y of n, you can write equal to mod of x of t. Mod of x of t. Okay, so my example is y of t. So I am writing here. Here I am writing. Consider y of t equal to mod of x of t. Mod of x of t. Say whether this is invertible or non-invertible. Seeing it, I can say this is non-invertible. This is non-invertible. There is no need to do everything. I will explain roughly. So for the input, x of t equal to 1. The output, y of t equal to 1. For the input, x of t equal to minus 1. Minus 1 mod. Minus 1 also becomes as 1 if it is a mod. Okay. So output, y of t equal to 1. So x of t equal to minus 2. The output y of t equal to 2 because minus 2, mod of minus 2 is 2. for the input x of t equal to 2, x of t equal to 2, the output is 2. Say simply, here my example is y of t equal to mod x of t. For negative values or the positive values, plus 1, minus 1, the answer is only the positive one. I can take the negative values or the positive values, the output is a positive value. That is, for minus 1 and plus 1, I am getting 1. Minus 2 and plus 2, I am getting 2. Minus 3 and plus 3, I am getting 3. That is, for different inputs, I have only one output. That is many to one mapping. That is, the input does not appear at the output exactly. That is, if the output is known, I can't find out the exact input because output is 1. I doesn't know the exact input. It is plus 1 or minus 1. I doesn't know the exact input. That is, there is no unique relationship between input and output. Hence, this system is an example of non-invertible system. Non-invertible system. Okay. So simple examples. So in this way, we can go for a number of examples. I hope you are all clear with this invertible and non-invertible system. So I explained clearly everything. Now, with this, I finished the classification of systems. I finished the topic classification of systems. So, in this class, what we discussed, we will go for the summary of today's class. Now, I will explain the summary of today's class. What I explained up to now. Okay, I will go for the summary of today's class. Summary of today's class. So, first, in this class, I explained you about the last two classification of systems. Last two classification of systems. Those are stable and unstable systems, and then invertible and non-invertible systems. So, in the summary, the first one is stable. Okay, stable and unstable systems. Stable and unstable systems. I explained about stable and unstable. First, I started with what is a stable system and then what is an unstable system. In that, I explained you BIBO stable. So bounded input, bounded output, and then what is bounded signal, and then I gone for what is a bounded signal, and then I explained an unbounded signal. Okay, I had given an examples for bounded signals and unbounded signals. So I given some graphical examples for bounded and unbounded signals. I had given some graphical examples for bounded and unbounded signals, graphical examples, and then I gone for the equation formats for stable and unstable. So if it satisfies that equation, then that is stable, and if it satisfies this equation, that is unstable. So I explained in terms of equation format. That is, the value, the input should be the finite and the output should be the finite. Okay, for a finite input we have to get finite output. That is, for a bounded input we have to get bounded output for stable, and for a bounded input if you get the unbounded output, that is unstable. I explained you with respect to the equation format, and then I gone for the graphical representation examples. Graphical representation examples for stable and unstable systems. For stable and unstable systems, I went for the graphical representation examples. Graphical representation examples. Okay. So, complete. I had given the examples, system example with taking some bounded and with the help of some bounded and unbounded signals. I had given you the complete example, graphical representation example for stable and unstable systems. Okay. And lastly, I went for problems, examples. Okay, so I have given some system equations. I have given different system equations. So based on system equations, I did the problem solving and I find out whether the system is stable or unstable. So I gone for the examples, problems. Okay, so there I have given different system equations. I solved it and find out whether the system is stable or unstable. So I explained this for both continuous and discrete. First I explained everything with respect to continuous, and later I gone for the discrete. So in problems also I did both for continuous as well as discrete. Okay, so almost the continuous and discrete are almost same, only the change is in variable. In continuous it is small t, and in discrete it is small n. So that is the first part. That's the first stable and unstable system classification. And then next I went for invertible and invertible and non-invertible systems. Invertible and non-invertible systems. Okay, so here also first I had given two definitions for invertible systems, and I given two definitions for non-invertible systems, and I have given some mappings, one-to-one mapping, many-to-one mapping, different mappings for your better understanding, and I have gone for them tabular formats. Okay, and then I gone for the small block diagram representations and equational representations for this invertible and non-invertible. So I gone in tabular forms, block diagram representation, graphical way, okay, and equation, everything. I explained this invertible and non-invertible system in many ways for your better understanding. So that if you remember that block diagram representation and equation representation, you can thoroughly get this invertible and non-invertible simply. So equation I had written like inverse transformation of x of t or x of n is equal to x of t, then it is invertible. If it is not equal to, if this one is not equal to, then it is non-invertible. I explained everything. Okay, and this explanation, after this explanation I have gone for some example problems. I had taken 3 system equations. Okay, 3 or 4 example system equations. Based on system equations, I had to identify whether the system is invertible or non-invertible. So I explained the concept of invertible and non-invertible system with the help of set problems. Okay, so I had taken system equation and I solved the system equation, and finally I said the system is either invertible or non-invertible systems. Okay, so this is what we explained in today's class. Okay, with this we completed the classification of systems. So before closing that, I explained this invertible and non-invertible for continuous time, and at the end I explained this for discrete also. Okay, at the end I explained it for discrete also. I am specifying once again, only the difference between continuous and discrete is the variable. In many cases, just by replacing the small t variable with the small n, we can convert the system from continuous to discrete in many cases. Okay, so if there are cases like that, I will explain with respect to continuous for our time saving purpose. Okay, only this is the only one I have to mention. So this is today's class. With this I am finishing the class, and with this I finish the classification of systems, and our next topic is operation on signals. So operation on signals we will see in the next class. Okay, thank you.